Hello everyone, my name is Amritanshu Rana and this is my video assignment for EE-230 course. The topic of this video assignment is Bernoulli and Binomial Random Variable, which is based off of the lecture 10 of EE-230 course. We'll be going over Bernoulli random variable, binomial random variable and a sample question. A Bernoulli random variable is the simplest kind of random variable. It can take on two values, 1 and 0. It takes on a 1 if an experiment with probability p resulted in a success and a 0 otherwise. Probability mass function will be p x equals to 1 will be equal to p and p of x equals to 0 will be equal to 1 minus p. A binomial random variable is a random variable that represents the number of success in n successive independent trials of a Bernoulli experiment. If x is a binomial random variable, we denote this x distributed over b in n, p, where p is the probability of success and n being the number of trials. Probability mass function p x equals to k will be equal to n choose k p to the power k 1 minus p whole to the power n minus k. If k belongs to natural numbers and k is greater than equal to 0 and less than equal to n, it will be 0 otherwise. Moving on to our sample question, a communication system consists of n components, each of which will independently function with probability p. The total system will be able to operate effectively if at least one half of its components function. The main question being that, in general, when is a 2k plus 1 component system better than a 2k minus 1 component system? Moving on to the solution, firstly we assume x to be a binomial random variable for the first 2k minus 1 components. A 2k plus 1 component system will operate effectively if x is greater than or equal to 2k plus 1 divided by 2. Similarly, for a 2k minus 1 component system will function effectively if x is greater than or equal to 2k minus 1 by 2. And it had been already mentioned in the question that total system will be able to operate effectively if at least one half of its components function. Further, p of 2k plus 1 effective basically means that out of all the 2k plus 1 components, at least k plus 1 effective components are there, which can be written as p of x greater than equal to k plus 1 plus p of x equal to k minus 1 multiplied by p square plus p of x equal to k multiplied by 1 minus p whole to the power 2, which we will be labeling as equation 1. Note that all the case above have 2k plus 1 components. And then understanding these elements in this equation 1, for x greater than equal to k plus 1, we have at least k plus 1 working components out of the 2k minus 1 components, because we assumed x to be a binomial random variable for the first 2k minus 1 components. Moving on to the x equals to k minus 1 part, here if x equals to k minus 1, so k minus 1 components out of 2k minus 1 are working effectively. So we want the next two components to function effectively too, making a total of 2k plus 1 components. So we multiplied the probability by p square, which basically means 2c2 multiplied by p square into 1 minus p whole to the power 0. Moving on to the third part, when x equals to k, if x equals to k, this means that k out of 2k minus 1 components are working effectively. So at least one of the two remaining components, since total number of components is 2k minus 1, when 2 is added to it, it will be equal to 2k plus 1, must function. So we multiplied it with the probability of at least one of the components is functioning, which will be equal to 1 minus probability of neither the components functioning. And mathematically it can be written as 1 minus 2c0 p to the power 0 1 minus p whole to the power 2, which can be written as this equation right here. Further, p of 2k minus 1 effective is basically when out of the 2k minus 1 components, at least k effective components are there, which will be equal to p of x equals to k plus p of x greater than equal to k plus 1, and we'll be labeling it as equation number 2. For the 2k plus 1 component system to be better than a 2k minus 1 component system, equation 1 has to be greater than equation 2. Hence, when we subtract equation 2 from equation 1, it should be greater than 0. As we do so, P of 2k plus 1 effective minus P of 2k minus 1 effective, we'll get these equations right here. Solving on these equations with simple algebra, we'll end up on the result of P greater than 1 by 2. Note that in the equation which is highlighted with pink color, we can observe that we had two binomial expressions, one of 2k minus 1 ck minus 1 and other of 2k minus 1 ck. But effectively, we can see that both of them are equal, so we can take them common in the next step. Further, in the step highlighted in green color, we can observe that we have a term of 2p minus 1, from which we can calculate the inequality of p greater than 1 by 2. Hence, for a 2k plus 1 component system to be better than a 2k minus 1 component system, the probability has to be greater than half. That was it from my side. Thank you.